An alternate form of trying to get numerical stability out of the system is to expand this perturbing force in series. Again, here we are going to be neglecting the mutual interactions of the perturbing bodies, and we are going to assume that all of the bodies are distant, so any ratio of R2RLJ over RJRL1 will be small. Because this is a strictly conservative system, we know that we can write this as negative the gradient of a scalar potential. And we are going to absorb that negative into our potential function, which we will call R sub j. And R sub j is called the disturbing function. And this is an incredibly important quantity that we're going to return to time and again. Looking at this term here, we can write R2RLJ divided by R2RLJ norm cubed plus RJRL1 divided by norm RJRL1 cubed is the same as the negative gradient of 1 over norm R2RLJ minus 1 over norm RJRL1 cubed times R2RL1 dotted into RJRL1. So everything here is a scalar. If you carry out this gradient in three-dimensional, for example, Cartesian coordinates, you will regain this expression here. And I urge you all to verify that this is true. And so we define our scalar function R sub j as gmj times that argument of the gradient that we just wrote down. Our differential equations for the orbit of our second mass around the primary first mass are now given by the standard two-body equation, and on the right-hand side, the gradient of the sum of all of the disturbing functions due to the various perturbing bodies. And again, we are neglecting the interaction between those bodies. What this buys us is that we can write a form of this disturbing function summation that makes it very easy to expand in series. And we do so in a couple of steps. First, we are going to rewrite the disturbing function itself as gmj over RJRL1 scalar, where this is the norm of the vector RJRL1, times RJRL1 over R2RLJ minus nu sub j x sub j, where nu sub j is defined as the cosine of that angle alpha sub j. And remember, the definition of this angle was the angle between R2RL1 and RJRL1. So cosine of alpha j is R2RL1 dotted into RJRL1 divided by their product of their magnitudes. X sub j is just going to be the ratio of R2RL1 to RJRL1. With these definitions, we can write the q function, q sub j, as xj squared minus 2 nu sub j x sub j. If we apply the law of cosines to the triangle formed by R2RL1, R2RLJ, and RJRL1, we find that the ratio of RJRL1 to R2RLJ is equivalent to 1 plus qj to the negative 1/2 power. This allows us to apply the binomial expansion, which is just a special case of Newton's generalized binomial theorem, which we've already used a couple of times. So that looks like one plus q sub j to the negative 1/2 power is the infinite sum for some dummy index k going from 0 to infinity of negative 1/2 choose k times q sub j to the kth power. Remember, this series is going to be absolutely convergent in the case where the absolute value of q is less than 1. We can further FOIL out the negative 1/2 choose k term, and so this becomes the infinite sum of negative 1 to the k times 2k factorial over 2k times k factorial quantity squared times q sub j to the kth power. So what is this q sub j to the kth power? Well, remember that we wrote q sub j as xj squared minus 2 nu j xj, which means that qj to the kth power is this whole expression to the kth power. Factoring out an xj to the kth power term from this, we can also expand this in series to get a kth order polynomial of the form that is qj to the kth power is xj to the kth power times the sum from a new dummy index L, 0 to k, of k factorial over k factorial k minus L factorial xj to the L times negative 2 nu j to the k minus L power. We take this, we plug it into here, and we now have one over the square root of 1 plus q sub j is equal to the double summation k equals 0 to infinity, L equals 0 to k of negative 1 to the L, 2k quantity factorial over 2 to the k plus L, k factorial, k minus L factorial, all times x sub j to the k plus L power times quantity negative 2 nu sub j to the k minus L power. If we rearrange some of these indices, we can turn this into the expression given here, where this first summation is still k from 0 to infinity. L goes from 0 to the floor function of k over 2, where you will recall the floor function is given by k over 2 when k is even and k minus 1 over 2 when k is odd. And the argument of the summation becomes negative 1 to the L times 2k minus 2L quantity factorial over 2 to the k L factorial times k minus L factorial times k minus 2L factorial times nu sub j to the k minus 2L power times x sub j to the kth power. Why did we do any of this? Well, the inner sum of this double summation is exactly the quantity defined by a Legendre polynomial, p sub k of nu k. So let's briefly remind ourselves about Legendre polynomials. Legendre polynomials are solutions to Legendre's differential equation, which has the form d by dx of 1 minus x squared times d by dx of Pn of x plus n squared plus n, Pn of x equals 0. We can find the solutions to this from something known as Rodriguez formula, which tells us that the kth Legendre polynomial of argument nu is equal to 1 over 2 to the k factorial times the kth derivative in nu of the expression nu squared minus 1 to the k power. And this can be rewritten as a sum from n equals 0 to k of k choose n quantity squared times nu minus 1 to the k minus n power times nu plus 1 to the nth power, all scaled by 2 to the k. We can also get to the same result from something known as the generating function, which is given by 1 minus 2 nu x plus x squared to the negative 1/2 power, which similarly produces an infinite sum in the Legendre polynomials of the form sum of k equals 0 to infinity of p sub k of nu times x to the k. And so you will recognize that this is exactly the form that we ended up with after all of our various mangling of the disturbing function. From this generating function, we can find that the kth Legendre polynomial of argument negative nu is equivalent to the kth Legendre polynomial of that same argument positive nu times negative 1 to the kth power. If we're generating these recursively, then the starting point for all Legendre polynomials, p sub k of 1 is 1, and so p sub k of negative 1 is negative 1 to the k by this formula. We can also derive several recurrence formulas, which I'm just giving to you here, along with equations that tell us how to find the derivative of pk. So this pk prime is the derivative of pk in nu, which means that you can recursively find the derivatives to any order. Legendre polynomials are incredibly important because they pop up in several contexts that we are going to return to, and in particular, in the solution of Laplace's equations in spherical coordinates. So we are 100% going to see these again and again as we move forward, and they are going to prove to be very useful tools whenever we need to do series expansions of specific types. Returning to the disturbing function, we can now write the jth disturbing function, which we originally defined as the gravitational constant times the mass of the jth perturber times the quantity 1 over the distance between our orbiting body and the jth perturber minus 1 over the distance between the jth perturber and the central body cubed times the radius vector r2l1 dotted into the radius vector rjl1. This is equal to gmj over scalar rjl1 times 1 plus the infinite sum from k equals 0 to infinity of the kth Legendre polynomial, whose argument is cosine of alpha j, which we've called nu sub j, times r2l1 over rjl1, which we've called x sub j to the kth power. our governing differential equation for the orbital motion of the second body about the first body as perturbed by n minus 2 mutually non-interacting other perturbing bodies is now the double summation over a set of derivatives of the Legendre polynomials, which we know we can recursively generate from the Legendre polynomials themselves. This looks awful, but it's actually relatively straightforward to calculate because modern software allows you to generate the values of these Legendre polynomials to essentially any order to machine precision very, very rapidly. And what we've gained here is that we have come up with a set of equations that are entirely independent of the quantity R2 rel J, which, as you will recall, is the term that is most likely to get us into trouble. If we assume that the perturbing masses are on very stable orbits that aren't really being themselves perturbed and that we can project them out for very long periods of time, as is true, for example, for the outer solar system, then we know the RJRL1 terms. We can just write them down. And we no longer need to subtract our position R2L1 from those terms because we have created a set of equations that are independent of R2LJ. So what this buys us is quite a lot of numerical stability and very rapid convergence of this interior summation so that for the majority of applications, we only need to use just a handful of the terms of these Legendre polynomials in order to get a very accurate answer that is also very numerically precise because it fits well into whatever data type we're using for our encoding.